Hello guys, welcome to the DMS online school. This video is a continuation from where we ended. Remember, we are in our revision phase, and in science paper 1 we started revising science paper 1 from the last topic, which is radioactivity. So we have done revisions already on science paper 1, the one which came in 2024 GCE and also internals, and this is the 2023 paper, and we are still covering radioactivity. So this is actually science paper 1 2023 for GCE. All right. So as I said in the last video which we did, that a question on radioactivity always comes from section B, and it is always on number 9, B9. As you can see also in this 2023 paper, we have found a question on radioactivity on B9. So let's read the question right away. So it says figure B 9.1 shows the radiations P, Q, and R passing through an electric field. Okay, so this figure that we have here is figure B 9.1. And what we are told is that there is radiation P, Q, and R, which is passing through magnetic fields. So these are magnetic fields that are going into the page. And this is the positive side of the magnetic fields, and this is the negative side of the magnetic fields. Okay, and then this is a radioactive source. So this is a radioactive source or material which is actually kept in its keeping place. So it is emitting three kinds of radiation, P, Q, and R, which are passing through the magnetic fields, with this being negative and then this one being positive. Okay, then question A says identify the emission P and the Q. So we need to identify the emission P, which is this one, and then Q, which is this one. So what we are going to do to be able to identify these is to understand some of the properties of these radiations, okay, or these emissions, okay, like what happens when they pass through a magnetic field or electric field. So remember, like we did in our previous lesson, where we said the alpha particles have got a small deflection, while beta particles have a larger deflection, and then gamma rays are undeflected when passing in an electric field. So in this case, when we look at P and the R, which one has undergone a much large deflection? It's actually P, all right? And then which one has not undergone a deflection? It's actually Q. And which one has undergone a smaller deflection? It's actually R here. Now we have at least been given that this side where R went, it is negative, and this side where P went, it is positive. So the one which has a much deflection, as we know from the theory, the lessons that we did and revised, the one which has got a larger deflection in magnetic field or electric field is actually beta particle. And by nature, in terms of charge, beta particles are negatively charged. And because they are negatively charged, they are attracted to the negative side of the electric field. So they will go to the positive side. Since they are negatively charged, they will go to the positive side of the electric field. So P is beta, because beta being negative, they will go to the positive, because unlike charges attract, positive attract negative. So if this is a beta particle which is negative, it will definitely be attracted to the positive. And then Q, which does not get deflected, is neutral. It has no charge. So this is gamma ray. and then R, which gets deflected to the negative terminal or negative side, is actually alpha particle, because alpha particles are positively charged and they can only go to the negative charge because there will be that attraction between positive and the negative. So R is alpha, then Q is gamma, then P is beta. So when A said identify the emission P and Q, then P, we are going to say that P is actually beta particle, and then Q is actually gamma radiation. Then they're saying B, give one use of emission Q. So like we give one use of emission Q, which is gamma radiation. The first use that you can mention is to treat cancer or radiotherapy. Okay, so the process of treating cancer is known as radiotherapy. So one use of emission Q, which is gamma, is to treat cancer. Then you could also mention that it can be used to check for leaks or flaws in metal pipes. So this gamma can be used to check for leaks, whether pipes are leaking or have got flaws in them. Okay, so it can also be used to sterilize medical equipment like syringes or bandages. So the word sterilize is similar to the word sanitize. Like during COVID-19, we were used to sanitizing our hands by washing with the alcohol so that alcohol can kill the bacteria. Now, gamma radiation is used to kill bacteria. So that process of killing bacteria using gamma ray or radiation is what we call sterilization. So gamma radiation is used to sterilize medical equipment like syringes and bandages, okay, so that they have no bacteria at all. All right, so let's proceed to the next question. So the next question, which is C, says mention two differences between emissions P and Q. So we need to mention two differences between emission P and the R. Emission P and the R. So here, what we are going to look at the differences are that number one, since emission P has been attracted to the positive, then emission P is positively charged. I mean negatively charged. Then since emission R has been attracted to the negative charge, it means it is positively charged. So we can say that emission P is negatively charged because it is attracted to the positive, while emission R is positively charged because it has been attracted to the negative charge. We can also say another difference is that emission P has less mass compared to emission R. Why? Because beta particles, emission P is a beta particle, and then emission R is alpha. So by nature, alpha particles are more heavier than beta particles. So this is why you can see that in terms of deflection, these are lighter and have been deflected much as compared to the alpha particles, which are heavier. So now in putting our answers, the first answer is that emission P is negatively charged while emission R is positively charged. Then the second difference is that emission P has a very small mass while emission R is much heavier. Okay, so this is the question which came from section B number 9 in 2020 3 science paper 1 GCE. Then we go to section C. Section C, we had this question C3. Figure C3.1 shows an apparatus used by a grade 12 learner to detect radioactive emissions. Background radiation was among the emissions detected. So this is an apparatus in figure C3.1. So we have a radioactive source here which emits radiation. So this is a detector which detects this radiation and sends the signal to the counter which reads the radiation here. So we are told that background radiation was also detected in here and registered here. So M says A Roman numeral 1, state what is meant by background radiation. Remember, we also covered this one in the previous revision. Then 2, give one example of a background radiation. Okay, so this is the first question. We'll look at them later. Let's go to the next question. Then B says table C3.2 shows the results obtained from the experiment after taking account of background radiation. Okay, so in that experiment which is here, whatever was recorded, whatever was counted by the counter here was recorded in this table. So there was count rate, how much it was counting, like this machine, how much it was counting per minute is known as count rate. When the radiation comes from here is detected, it is sent here. So how much radiation was counted, was recorded per minute, was counted as numbers and was recorded like. So at the beginning, count rate. This we have count rate, which is counts per minute, and then we have time in minutes. At the beginning, before the counting started, radiation count on that counter was 200 count per minute. Okay. Then later, after 30 minutes, it counted 100 counts. Again later, after another 30 minutes went to 60, it counted 50. Again after 30, another 30 minutes went to 60, total time 25. Again after 30 minutes, it went to 120, it counted 12.5. Then Roman numeral 1, plot a graph of count rate, this count rate, in count per minute against time in minutes, 4 marks. Then B, from the graph, determine the half-life, 2 marks. Then this is Roman numeral 1, Roman numeral 2, Roman numeral 3. What fraction will have decayed at 120 minutes? So at 120 minutes, what fraction would have decayed? Then C, a nucleus of uranium-235, which is this one, emits one alpha particle to form thorium, which is TH. Write an equation for this decay, 1 mark. Alright, let's now proceed in answering. So we'll start with the first question, which says, state what is meant by background radiation. Remember what we said? We said the background radiation is the low amount of radiation that is always present in our environment in the absence of a radioactive material. So just as I said in the previous revision that there is always that radiation in the environment even when we do not have an active radioactive material there. So that radiation which is present, we call it background radiation. Alright, so if you're enjoying, guys, give this video a like and also let me know in the comment section. And for those of you who would want to join the online revisions, you can WhatsApp me on the number 0977 9241 75 0977 9241 75 so that you can be part of this great and detailed revision. Alright, so let's proceed. So we go to the second question, which said give one example of a background radiation. So there are many examples that I also gave in the previous revision and also in this revision. The first one, we can say cosmic rays from the sun and outer space. So the sun emits cosmic rays that scatters throughout the universe. Okay. Okay, so cosmic rays from the sun and outer space. So as I was saying, the sun releases rays which are known as cosmic rays, those that go out in space. So some of them come from other stars in the universe, and those provide or contribute to what is known as background radiation. Okay. Then another source or example is radon gas from rocks and the soil. So rocks also and soil also release background radiation, and one of the uh, atom that is there is actually radon. Then radiation from food and the drink. So food that we eat and some drinks contain radiation. For example, radiation comes from uh, carbon 12. I mean carbon 14. Though the radiation is low because the half-life for carbon 14 is actually a quite a long one. So it releases low-level radiation. All right. So another one is radiation from man-made sources like nuclear tests that are done especially in advanced countries like in Iran. So far there have been bombing there to stop nuclear enrichment, which is developed to be one of the ingredients that is used to create atomic bombs. Okay, so and also medical raids. Okay, so these are some of the examples of background radiation in case a question comes and asks you to give examples of background radiation. Then let's move to the next question, which is C3B1, where they are asking to plot a graph of count rate against time, and this is 4 marks. So for you to be able to acquire all these 4 marks that are provided here, you need to do these things here. So to get all 4 marks, you must do the following on your graph paper. So you have axis and the labels. So the axis and their labels, like you draw the y-axis and the x-axis, you label them, you get 1. Like draw the y-axis for count rate. So you draw the y-axis, you label it count rate or counts per minute, and also the x-axis, and then you label it time in minutes. Then the scale also will make you acquire 1 mark, a scale. So you will know what a scale is uh, in the next slide. So here choose a sensible scale that uses at least half of the graph paper. So when you are given a graph paper, at least your graph should cover at least more than half of the graph paper. Okay, then you need to plot. Plotting itself is 1 mark. So where you carefully mark all the points from the table with a neat X curve, like X like that. Usually it is X or dot is also allowed. So then you draw a smooth best fit curve that passes through or close to all the points. Then you do not connect the dots with a ruler like a zigzag line. Okay, so some people may connect the points. You should know when to use a ruler and when to not use the ruler. Like graphs on half-life are not supposed to have to be drawn using a ruler. They're supposed to be points connected by just a hand free. So it must be a curve. Okay. So now let's go ahead with the plotting. So with me, I have an examination graph paper here, part of the examination graph paper. So this is a standard examination ECZ um, graph paper. So what you need to have is to label actually your title. The graph must have a title like count rate against time. That's what you are plotting for. Then you need to label your axis. Okay, like your axis here, which is the vertical axis, which is the y-axis, should be counts per minute, and then your horizontal axis, which is the x-axis, should be time in minutes. Okay, then you draw a line, the x-axis like that, and then you draw the y-axis like that. So once you do like that, then you need to look at the scale. So the scale before the scale, this is the data that you need to plot. Count rate, which is minutes per count, which is counts per minute, and then time in minutes here. So these are the axes. You label like that. Then now you choose a scale. The scale which you choose must be able to accommodate the values for that particular axis. For instance, the scale that you choose for the for the y-axis must be able to accommodate the values that you're supposed to put in the y-axis. So the largest value that you are to put in the y-axis is actually 200 counts per minute. So it must move, the values must move up to 200 here, must be able to accommodate 200. Then on the time, which is the x-axis, the largest value you have to put there is 120. So you must ensure that you choose a scale that is able to accommodate values from 0 up to 120. So for me, this is what I did. So I looked at this here. I counted them 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10. That one. I said if I give each box here is actually 2 centimeters. If I say this box here should be 2 centimeters, which is 2 centimeters should be 10. I said if this is 10, then 20, 30, 40, 50, 60, 70, 80, 90, 100. Will I be able to reach 200? No, I've only gone up to 100. Then I said, okay, if I say 20, I say, okay, if this is 20, then 40, then 60, 80, then 100, 120, 140, 160, 180, then 200. So this one could have also worked. However, I avoided it because of not leaving any space this side here. So I said 20, 40, 60, 80, 100. Then 200, 220, 120, 140, 160, 180, then 200. I avoided that one because I wanted to leave space here. Okay. Then what did I choose? So what I've done here is actually okay. When you use 20, it's okay. 20 to represent one box. From here to here, 20. Then you add another 20, 40, another 20, 60, another 28, another 20, 100, another 20, 120, another 20, 140, another 20, 160, another 20, 180, another 20, 200. So it can fit if you use 20, but I didn't use that one. Then on this one, you have 0 up to 120. So you could choose, if you say 10, if you say from here to here, it should be 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Here, it couldn't fit because you are going up to 120. So if you want, you can also say, maybe you say 20, then 40, but what I used was 15. One box was 15. So from here to here, 15, up, and then you add 15, 30, then 45, then you go to 70, just like that. So now, let's see what I did with the scale now. So the scale was like, in the x-axis, 2 centimeter, which is one box is 2 centimeter, was given 15 minutes. So from here up to here was 15 minutes. From here, 15 minutes, from here, 15 minutes, from here, 15 minutes, from here, 15 minutes. Just like that, it went on accumulating. So if you put from here 15 minutes to here, you add another 15 minutes, you add another 15 minutes, so that the intervals are the same. The differences from one point to another are the same. Then another scale which I used on the y-axis here, I said 2 centimeter, which is one box, is equal to 25 counts. Like if from here to here 25, from there to there another 25.50, from there to there another 25.75, just like that. So this is what I did. So I start with 0 here, then I said 25, 50, 75, 100, 125, 150, 175, 200. At least it went up to that level. Then from here I used 15. So the first one is 15, 15, then 30, then 45, then 60, then 75, then 90, then 105, then 120. So we are able to accommodate 120. Then after that, you have seen that that has been done. Now you can begin plotting. So you start plotting these values here like pairs. 0 with 200, 30 with 100, 60 with 50, 90 with 25, then 120 with 12.5. So we started. So we did 0 with 100. So 0 is here, comma 200 is there. So the point will be there. Then we came to 30 with 100. 30 is here. So 100 is here. So I mean 100 is here. Okay. So it will be there. Then we did 60. 60 with 50. So 60 is here, 50 is here, as you can see. So we did like that. Then 90, 25. 90 is here, 25 is here. So like that. Then 120 with 12.5. So 120 is here. 12.5 is the middle of 25 and 0. So the middle part here is here. Okay. Then after that, you now connect the points using a free hand like that. So this is the graph that you need to plot for you to get all the 4 marks. Then we move to the next question. From the graph, determine the half-life, 2 marks. So from that graph which you have plotted here, how do you determine the half-life? So you just determine the half-life like this. So you get the full count rate, you half it. Half of the full count rate given here is 100. So you come per 100, you draw a line. When the line touches the curve, where it touches the curve, you draw a line down. Where it points, that's where half-life is. So you can say now that the half-life is 30 minutes. You can even put the answer on the graph. Yeah, so now from the graph determine the half-life. So we are saying half-life is 30 minutes. Then another question said, what fraction will have decayed at 120 minutes? So like at 120 minutes, what fraction would have decayed? So to find the fraction which would have decayed, you say initial count was actually 200 in that table. Then final count was 12.5. So where have I found 12.5? Let me just go back and show you where I have found 12.5. So you see, after 120 minutes, this is in minutes 120, the count is at 12.5. After 120, it is 12.5. That is the final. The remaining, the initial count was 200, then the final is 12.5. That's where I'm getting those values. Okay. So now fraction remaining. Initial count 12, final 12.5. Fraction remaining, because the question is saying what fraction will have decayed at 120. So now the fraction remaining now is going to be equal to, you get 12.5 over 200, which will give you 6 over 16. I mean 1 over 16. Then from there, fraction remaining now, it will be, you get the 1 minus 1 over 16, you get 15 over 16. That is the answer. Then we move to the next question, which is the last one. It says a nucleus of uranium-235 emits one alpha particle to form thorium. Write an equation for this decay. So we have uranium-235 which emits one alpha particle to form thorium. Write an equation for this decay. So remember, an alpha particle is a helium nuclide. So we know what it is, a helium nuclide. So the general equation, like I showed you in the previous revision, was that the general equation, if you have a parent atom that is undergoing decay by emitting alpha particle, it will give you a daughter particle. Sorry, I didn't put X, it's supposed to be Y. So it will give you a daughter particle. Now, the daughter particle's atomic mass would have reduced by 4. So you get the atomic mass of the parent minus 4 to get the atomic mass of the daughter. To get the atomic number of the daughter also, you get the atomic number of the parent minus 2. Then plus now an alpha particle. So in this case, an alpha particle can be represented by a helium nuclide. So having this general equation in your mind, you can now begin with uranium. You start with uranium, which is this one, uranium 23592. So to get to thorium, now, for you to get thorium, here you subtract 235 minus 4, 92 minus 2, so that you get thorium. If you say 235 minus 4, you get 231. Then 92 minus 4, you get 90. Then plus, you get the helium here. So this is the decay equation they are asking for. Okay, so this is where we end with this very revision. Just as I said, if you want to be part of this great revision in science paper 1 and 2, you can WhatsApp me on the line on the screen there, so that you can be helped to do well in these coming exams. For now, guys, bye and see you in the next revision. Peace.